Okay, so in this lecture, we will apply the mole balance for the CSTR. So here's the balance that we derived previously. The volume is equal to FA naught minus FA divided by minus RA. Or in other words, the reactor volume is equal to the amount of species A reacted in the reactor divided by the rate of consumption of species A. So if species A is a reactant, that means the rate of consumption is positive. If species A is a product, that means that the rate of consumption is negative. Additionally, if A is a reactant, that means that the amount leaving the reactor is less than the amount entering. So this numerator here is positive. If A is a product, that means the amount leaving the reactor is going to be greater than the amount entering, so the numerator is going to be negative. So the point of all of this is that the accounting checks out. The volume in either case is going to be positive. So part of writing and applying mole balances is making sure that the terms that we're using result in situations that we expect. So in this case, we expect a volume to be positive, and henceforth we want to make sure that all of the terms enter in a way that are combined to form or to combine to make a positive volume. So another way to look at this, so the reactor mole balance. So we have this numerator term and this denominator term. The numerator term gives the amount reacted. For example, if species A is a reactant species, then the numerator tells how much was reacted. If it's a product species, it tells how much was formed. But basically, if you want to react away a lot of species A, or if A is a product and you want to form a lot of species A, that tells us what about our reactor volume? We need a bigger volume or a smaller volume? So we're going to need a larger volume. So the more we want to react away or the more we want to form, the more volume that we're going to need. If we look at this rate of consumption, so a faster reaction rate would be a larger rate of consumption, and a slower reaction rate would be a smaller rate of consumption. What does this tell us? If the rate of consumption is larger, do we need a smaller or a larger volume? So the faster the rate, the smaller the volume that we need. So if the rate of consumption is larger, the volume needed is smaller. So that's the mole balance in terms of flow rates. This is the mole balance in terms of conversion. Basically, it's saying the same thing. The numerator is the amount that's been reacted away, and then the denominator is the rate of consumption of A. If we're going to use this form of the balance, then we need to convert all of the concentration terms in this rate expression into conversion, because just like in the case of the batch reactor, we don't want to convolute terms. We're either going to write in terms of X or in terms of F, but we can't have combinations of both. So just like with the batch reactor, if you're solving problems involving CSTRs and you're using a prototypical CSTR, so following all of the assumptions that we wrote down for the CSTR, you can just write down the appropriate form of the mole balance, either in terms of flow rate or in terms of conversion. You don't have to derive it each time. The CSTR mole balance is pretty easy to derive, so if it's easier for you to just derive it each time, that's fine. In fact, that's what I usually do. But for the prototypical CSTR, it's fine just to write down the form of the balance that you intend to use. Just like with a batch reactor, there's two exceptions. Number one, if we ask you to derive the balance, then derive it. The other case is if the reactor is not a prototypical CSTR, and this should say CSTR. In that case, then the balance for the prototypical CSTR is not valid, so you'd have to derive the balance for the type of reactor that you have. But if you have a prototypical CSTR, you may feel free just to write down the correct form of the balance. So let's now do an example. Let's look at the liquid phase reaction A plus B goes to C, and we're going to carry this out isothermally in a 200 cubic decimeter CSTR. The reaction is going to run at 350 degrees K. And we'll say the feed is equal molar in A and B and no C is fed. And we want to determine the conversion that is possible in this reactor. So other information that we're given, a volumetric flow rate entering, a rate constant. Notice that the rate constant is given to us at 300 K, but the reaction temperature is 350 K. We're going to have to account for that. We're also given an activation energy and an initial concentration of A. So let's go ahead and solve this thing. First thing I'm going to do is draw my reactor. So here's my CSTR. Entering my reactor, I have A and B. And then exiting my reactor, I have A, B, and C. So I'm always writing my mole balance in terms of molar flow rates. So these are the F terms are molar flow rates. They're given they're in units of moles per unit time. But I'm not given the inlet flow rates in units of moles per unit time. Instead, I'm given a volumetric flow rate and a concentration. So I'm going to take that information. I'm going to say that FA naught is equal to V naught times CA naught. So moles per liter times liter per time should give me moles per time. This is a liquid phase reaction. Because of that, constant volumetric flow rate. So script V equals script V naught. And so this means I have enough information to determine my inlet molar flow rate. FA naught is equal to 10 cubic decimeters per minute times CA naught, which is 2 moles per decimeter cubed, which is going to give me 20 moles per minute. So the problem statement says that the feed is equal molar in A and B. That tells me that FB naught is equal to FA naught. And again, this is a situation where not only is the feed equal molar in A and B, but the reaction stoichiometry is equal molar in A and B. Henceforth, I expect the flow rate of B coming out of the reactor to be equal to the flow rate of A coming out of the reactor. So at every point along the system, the flow rates of A and B should be equal. Okay, so now I know these quantities. I have a reaction going on in here. So let's solve the mole balance. So the problem asks for me to determine the conversion. So I'm going to use the mole balance equation in terms of conversion. So V is equal to FA naught XA divided by minus RA. I'm not told anything about the rate law, so I need to do something about that. I'm going to say assume elementary kinetics. So we've said that when, in the absence of any other information in this class, if we need to make an assumption about a rate law, a good assumption is to say that the reaction is elementary. So I'm going to make that assumption, and part of my solution is I'm going to write that assumption down. And that's because if that's the wrong assumption, at least I have written that down so whoever goes and looks at this solution knows, oh, that's what Dr. Rachel did, was to assume elementary kinetics. I see where she's getting her solution now. So I'm going to make that assumption, assume elementary kinetics, and then I'm going to use that to write my rate law, K, CA CB. Writing this rate law, so I noticed that if I have elementary kinetics, that my rate law is equal to a rate constant times concentration squared. And if I go back and look at the units on my rate constant, I have inverse concentration per minute. So that makes a lot of sense. So that means that the units on my rate would be in terms of concentration per minute, and that's an appropriate set of units for a rate. So I know that my rate is going to be in units of moles per volume per time. So my rate constant here being in units of inverse concentration per time and then being multiplied by concentration squared, that's going to give me the right units. So this tells me that my assumption to write the rate law as in having elementary kinetics is probably a good assumption. Okay, so now I have an expression for the rate law. I have my mole balance here, but I'm stuck at the same point where I am usually getting, which is my mole balance is in terms of conversion and my rate law is in terms of concentration, and I can't convolute the two variables, so I got to write my concentrations in terms of conversion. So to do that, I'm going to go back to this. This is a liquid phase reaction. Because it's a liquid phase reaction, I know that I can write an expression for the concentration of A in terms of the conversion of A. And also, since I know that A and B are always equal molar, I can write that expression for, or I can equate the concentration of B to that of A. That means that my rate is going to be equal to K Ca naught squared 1 minus Xa squared. So now I can enter that into the mole balance. B is equal to Fa naught Xa divided by K times Ca naught squared times 1 minus Xa squared. And again, I don't have this value for Fa naught, so I'm going to write it as V, script V times Ca naught times Xa all over K Ca naught squared 1 minus Xa squared. And then I can further reduce this into script V times Xa divided by K Ca naught 1 minus Xa squared. So now I could theoretically solve this. I have a volume. I know what my volume is. I know what my volumetric flow rate is. X is what I'm solving for. I know what my inlet concentration is. I know what K is, but unfortunately I have K at the wrong temperature. I have K at 300 Kelvin and I need it at 350 Kelvin. So before I solve this equation, I need to get the correct value for K. So what equation am I going to use to do that? So I'm going to use the Arrhenius equation. So the Arrhenius equation, basically what I need to be able to get a rate constant, if I don't have a rate constant, what I need to be able to get that, I either need a pre-exponential term and an activation energy, or I need a activation energy and the value of a rate constant at another temperature. If I have either one of those things, I can solve for the rate constant at the temperature that I need. So the form of the Arrhenius equation that we'll use here says that the rate constant is a function of temperature is equal to the rate constant at some given temperature times the exponential of the activation energy divided by the gas constant times 1 divided by the given temperature minus 1 divided by the temperature that we're looking for. So in this case, this value was given. This is 85 kilojoules per mole. R is equal to 0.008314 kilojoules per mole Kelvin. This T naught is the value that we're given, the rate constant. So this is the 300 Kelvin. The T that we want to solve for is 350 Kelvin. And this value here, this K of T is equal to the value at 300. So this value right here. So we could fill all of that in. So it should give us our rate constant. I get a value of 8.447 cubic decimeters per mole per minute at 350 Kelvin. So I can sub that into my mole balance. And so doing that, I get V is equal to script V times XA divided by this K term, CA naught 1 minus XA squared. And this requires a quadratic solution, so you can solve it using the quadratic formula. If you, for example, multiply both sides by this quantity and then do some algebraic manipulation so that you get an equation in terms of that looks like 8x squared plus bx plus c equals 0. You could enter this equation into Microsoft Excel GoalSeek, or however you want to solve it. Let's say the numerical solution or the analytical solution. It's quadratic. However you obtain this solution is up to you. I do not expect you to solve this by hand. If you want to use your calculator or Excel or Python or whatever have you, go for it. So however you decide to solve that is fine with me. When I solve it, I get a conversion of 93%. So that's all I want to say about CSTR mole balances. The key concept here is that the solution is algebraic. So the harder part in terms of the CSTR mole balance is figuring out how to fill in all of the terms. If you can do that, the solutions are generally simpler than the batch reactor, the PFR, the PBR, or the other types of reactors that we'll get to later in the class, such as the semi-batch and the membrane reactor. All of those reactors require differential equation type solutions. The CSTR is a nice and easy algebraic solution.